We want to diagonalize a 3 by 3 matrix. 4, 3, negative 1, negative 3, negative 2, 1, negative 3, negative 3, 2. And we're going to start by, how do we always start? We start by looking at real eigenvalues. Here goes, eigenvalues. All right, so I'm going to look at what? The characteristic polynomial evaluated at lambda, determinant of a minus lambda I, set equal to 0. Which means we're going to take the descending diagonal and we're going to subtract lambda from it. So we're going to have what? Determinant of, so down the diagonal we're going to have 4 minus lambda, minus 2 minus lambda, and 2 minus lambda. And everything else stays the same. We get a minus 3, we get a minus 3, we get a minus 3, minus 1. Now that's a 3 there, right? That's a 3. Let me get rid of that. Make sure that's a 3. Come on, 3, where are you? 3, negative 1, 1. All right, so I got to calculate this determinant. This determinant is not the easiest determinant in the world to compute. It's going to be a little bit of work, So shall we expand across the first row? Yay, let's do it. So we're going to have what, a plus, a minus, and a plus here. I'm going to start off with a 4 minus a lambda. I'm going to take a determinant of a submatrix. So I will cover up the first row, first column. I'm going to get what? Minus 2 minus lambda. 2 minus lambda down the diagonal, and minus 3 and down 1. And then I'm going to have plus 3, right? The double negative makes plus 3. I'm going to look at the determinant of the submatrix. Cross out the first row, second column. I'm going to have what? 3, negative 1 down the first column. And negative 3, 2 minus lambda down the second column. And then I'm going to go to minus 3, determinant of submatrix. You cross out the first row and the third column. We're going to have what? 3, negative 1 on the first column, negative 2 minus lambda down the, what column is that? Second column, and then 1 down the second column. And that's all going to be equal to 0. So we clean this up a little bit. We're going to have what? 4 minus lambda. Let's take that first determinant. We're going to have, let's see. I'm going to put that in, put it in that color. So we're going to take what? Negative 2 minus lambda, 2 minus lambda. That's going to be plus 3, right? You take minus 1 times negative 3 is plus 3. So we're going to have plus 3. We're going to do in green, nice green. We're going to have what? 6 minus 3 lambda. That's when we take 3 times 2 minus lambda. And then we're going to what? Subtract negative 1 times negative 3. That's going to be subtracted 3. All right, and we're going to have minus 3 times the next determinant. Now that's equal to 0. Let's see, how do we do the determinant here? We're going to do 3 times 1 is 3. Minus, let's see, minus what? We take negative 1 times negative 2 minus lambda. We're going to get parentheses 2 plus lambda. That's a thing. All right, now can we clean up a little bit more? I'm saying yeah. In the green here, first we can do a little bit of foiling. We can foil this out, and when we foil that out, what are we going to get? We're going to get what? Negative 4 plus lambda squared. And we got what? Plus 3. And then what do we got? We got 3, and then we can clean up in this next parentheses or bracket. That's going to be what? If you combine the 6 and the minus 3, that's going to give us 3. We're going to have 3 minus 3 lambda. What else? We're going to have, what, minus 3, and we can clean this up here. What can we do? We can take 3 minus 2 is going to be 1, and then we're going to have a minus lambda. All that's equal to 0, right? So I keep going with my simplifying. And when I simplify in the first green bracket, I'm going to have, what, lambda squared and a minus 1. Right, if you combine a minus 4 and a positive 3, you get a minus 1. And then I got plus, make it blue, plus 3. And then I got a bracket. Here I can factor in here. I'm going to factor out a 3, and then there I got, what, 1 minus lambda when I factor the 3 out. All right, so it's going to be, what, minus 3, and then I got 1 minus lambda here, equal to 0. I don't know why I switched colors, but... All right, now, what do we got? What do we got? What do we got? We got, okay, 4 minus lambda. Come on, man, out of the way, out of the way. You're in the way. 4 minus lambda. Scoots you down. Scootsy, man, scootsy. All right, can we factor the dude in the blue brackets? That's going to be, what, lambda plus 1? Lambda minus 1? All right, what else can I do? I can say here that I got a 9, right? And I got, what, 1 minus lambda in parentheses, right? So the 3 times the 3 times the 3 gave me the 9. That leaves me with the 1 minus lambda in parentheses, and then I got a minus 3. Let me call that a bracket right there. Let's call that a bracket right there. And I got a bracket 1 minus lambda. And that's equal to 0, right? Equal to 0. Now, if you look over here, hey, looky here, man. This guy right here has a lambda minus 1. Okay, we'll worry about that a little later. It's kind of matching up with those 1 minus lambdas, right? Kind of. 4 minus lambda. And then we got what? Lambda plus 1. And then we got what? Lambda minus 1. Now what I'm going to do, I'm going to connect these guys, or combine those guys. 9, 1 minus lambda, minus 3, 1 minus lambda. That's going to give me a positive 6. 1 minus lambda, right? And that's equal to 0. Now, I'm saying these black 1 minus lambda and lambda minus 1, these look pretty similar, right? I'm going to underline them in yellow, actually. They're pretty similar. Not quite the same, though, right? They got different signs. So what I'm going to do here, I'm going to leave the 4 minus lambda. I'm going to leave the lambda plus 1. I'm going to leave the lambda minus 1 here. And what I'm going to do, you see that positive 6? I'm going to make that a negative 6. And I'm going to flip the signs on 1 minus lambda to make it lambda minus 1. And that's equal to 0. So now we got lambda minus 1s. So these guys have a lambda minus 1 in common now. So I'm going to factor that out front. I'm going to have a lambda minus 1 out front. In the big old bracket, I'm going to be left with, let's see, 4 minus lambda. Lambda plus 1. And then we're going to have a minus 6. Minus a 6. And all that's equal to 0. So what I'm going to do, I'm going to write down my lambda plus 1. Can you write down lambda plus 1? I'm sorry, lambda minus 1. And I'm going to expand inside my brackets here. Now that's equal to 0. How do you expand inside the bracket? You do a little bit of foiling, right? Foiling. How do you foil? You do what? 4 lambda. 4 plus 4 minus lambda squared, and then minus lambda. And oh, don't forget your minus 6. That's not part of the foiling process, but it's there anyhow. It looks like we got what? Lambda minus 1. And in brackets here we got what? Minus lambda squared. That's this dude. You combine your 4 lambda and your minus lambda. What's that? 4 lambda and minus lambda is positive 3 lambda. Then you combine your 4 and your minus 6, and you get minus 2. That's equal to 0. All right. So what I got to do now, I got to focus on factoring this this quadratic right here. What's this quadratic? This yellow dude. So what I'm going to do, I'm going to factor out a negative out of that. I'm going to pop it. I don't like that negative out in front of the lambda squared, so I'm going to factor out a negative. Or what you could do, you multiply both sides. I'm going to multiply both sides by negative 1. So I'm going to have lambda minus 1. When I multiply both sides by negative 1, I'm going to get what? Lambda squared minus 3 lambda plus 2. And on the right side, when I multiply by negative 1, it stays 0. All right. So now I can factor. We got what? Lambda minus 1. We factor the yellow guy into what? Lambda minus 2. Lambda minus 1. All that's equal to 0. So it looks like we get several. We get 2 eigenvalues, actually. We get lambda equals 1. This is going to have algebraic multiplicity of 2, right? Multiplicity of 1 is 2. And we're going to get what? Lambda equals 2. And that's going to have algebraic multiplicity. Multiplicity of 2 is going to be 1. All right, so it took all that work. Look at all that. All that work just to find the what? Eigenvalues. So now we're going to find the basis for the eigenspace of A associated with the eigenvalue 1. So what we're going to look at is A minus 1 I3 augmented with the 0 vector. I totally forgot what A was. Okay, so you got that matrix 4, negative 2, 2 on the main diagonal. You got to subtract 1 from that. So if I subtract 1 from that, 4, negative 2, 2, you're going to get what? 3, negative 3, 1. And all your other values are the same. So maybe I should put that in red. 3, negative 3, 1. That's the diagonal. So we subtracted 1 from the diagonal of A. And everything else stays the same. It's going to be what? Negative 3, negative 3, negative 3. What was this? 3, negative 1. I got it written down here. 1. And then here on the right, we got a column of zeros. Okay, so what do we do next? We row reduce this. Row reduce this. So you multiply row 1 by negative 1 and add it to row 2, and it cancels out row 2. You get zeros. And you multiply row 3 by 3 and add row 3 to that, and you get all zeros there. So this is going to end up being row reducible to 3, negative 3, negative 3, 0, 0, 0, 0, 0, 0, and then you got zeros down the right-hand column. So we want to find a general solution to this. General solution. All right, so we got 2 free variables, right? x2 and x3. x1, we can find x1 here. Use the top equation. We got what? 3x1 minus 3x2 minus 3x3 equals 0. So I believe that'll give x1 is what? x2 plus x3. x2 plus x3. All right, so the vector form of solution is going to be the vector x consisting of what? x2 plus 3 is the first entry, x2 is the second entry, x3 is the third entry, and we can factor out, putting in the parametric form, factor out an x2, and you get what? Vectors 1, 1, 0. And factor out an x3, and you get the vector what? 1, 0, 1. So your basis for the eigenspace here is going to consist of those two vectors. So this is a basis for eigenspace. What was the eigenvalue here? I totally forgot the eigenvalue. What was our eigenvalue? Was it 1? Yeah, eigenvalue was 1. Basis for the eigenspace associated with 1 is those two vectors. Set containing, we'll call it B1. Set containing those two vectors. What vectors? 1, 1, 0, 0, 1, 0, 1. Okay, let me write that again. 1, 1, 0. First vector, second vector is 1, 0, 1. So here we could say that our geometric multiplicity of the eigenvalue 1, the geometric multiplicity of the eigenvalue 1 is 2, because the eigenspace has dimension 2. So notice that the geometric multiplicity matches up with our algebraic multiplicity. Earlier, we said our algebraic multiplicity was 2, right? Because it had a repeated root. Repeated root right here, right? The algebraic multiplicity agrees with the geometric multiplicity. So far, we are diagonalizable. Let's check the second eigenspace. The eigenspace associated with the eigenvalue of 2. Dude, don't do that. Don't do that. Erase. Shouldn't be drawing. All right, let's look at a basis for the other eigenspace. See if we can get it in here. Basis for the eigenspace associated with the eigenvalue 2 of A. So we're going to look at what? A minus 2i3, augmented with the 0 vector. Focusing on that associated linear system. I have 0 vectors down the right-hand side there. Basically what we're doing, we're subtracting 2 off of the main diagonal of A. What's the main diagonal of A? 4, negative 2, 2. 4, negative 2, 2. So we're going to subtract. And you get what? Negative 2. No, 4, negative 2, 2 is going to give what? 2, negative 4, 0, right? 2, negative 4, 0. Okay. And I'm going to keep my other entries the same. Now I have this written down so I can, don't have to look back and forth. I got what? Negative 3 was the same. Negative 3 was the same. Negative 3 was the same. 3 was the same. Negative 1 was the same, and 1 was the same. Okay, so there's 2 minus I3 augmented with the 0 vector. It turns out you can RREF this. I'm going to go ahead and RREF this. It's not too easy to do. I'm going to RREF this. So let me RREF this. Use a calculator. RREF. When you RREF that, you end up getting 1, 0, 0. 0, 1, 0. 3, 3, 0. Augmented with the 0 vector. 0, 0, 0. Okay. So, for a general solution, and let's see. So it looks like we have a free variable, right? A free variable right here. So x3 is free. And x2 we can find, and x1 we can find, right? So x1, we can use this equation right here, the second row, and you're going to get x2 is equal to minus 3x3. And you can use the top row, and you can get x1 is minus 3x3. Now that's going to be your general solution in the vector form. Of the solution is going to be vector x takes on the form negative 3x3. negative 3x3, x3. And you can factor out the x3 parameter. It gives you negative 3, and 1. So that single vector there, that green vector I'm underlining right now, negative 3, 1, that's going to be a basis for the second eigenspace, E2 of A, right? The eigenspace associated with the eigenvalue of 2. We're going to call that B2 for the second basis. It's going to consist of a single vector, negative 3, and 1. Okay? So, notice we have 3 linearly independent eigenvectors here from these bases altogether, right? We have 2 bases, we have 3 linearly independent eigenvectors. So, since there are 3 linearly independent eigenvectors, then we have a diagonalization of A, since A has 3 linearly independent eigenvectors, then A is diagonalizable. Yep, and also, I mean, notice that the dimension of that second eigenspace is 1, right? The dimension of that second eigenspace, E2 of A, is 1. And it agrees with the algebraic multiplicity for 2, right? The algebraic multiplicity for the eigenvalue 2 is 1 as well. So the algebraic multiplicities agree with geometric multiplicity. So you could say, also you could say that algebraic multiplicity, which is m of 1, was 2, right? That's equal to the dimension of the eigenspace for 1. So this is the algebraic multiplicity agrees with the geometric multiplicity for the eigenvalue 1. This is for the eigenvalue of 1. They both had a multiplicity of 2. Algebraic multiplicity agreed with geometric multiplicity, and for the eigenvalue of 2, remember the algebraic multiplicity of 2 was 1. It only showed up once, that root, and the dimension of this eigenspace, E2 of A, that was 1 as well. So the right-hand side is called the geometric multiplicity. The left-hand side is called the algebraic multiplicity. When they all agree, then you're going to be diagonalizable. That's just something to keep in mind, something else you can think about. But in any case, it's diagonalizable. So the idea here is that A here, I'm going to write it down at the bottom of the diagonalization. The diagonalization is A equals P D P inverse, right? D, make it in blue, is going to be the diagonal matrix, where you put 1 twice down the diagonal, right? 1 occurs twice down the diagonal, because 1 had multiplicity 2, and 2 was the second eigenvalue that's going to occur once in the diagonal, and 0 goes everywhere else. And then P, what's P? You want to put P in the right order. You're going to have 3 columns, right? So your first column is going to be 1, 1, 0. Your second column is going to be 1, 0, 1. Those are coming from the eigenvectors, the linearly independent eigenvectors of 1, the eigenvalue 1. And then for the third column, you're going to put the linearly independent eigenvector for the eigenvalue 2, which is negative 3, 1. So this right here gives you the diagonalization of A. All that work just to get that little factorization.